Hello students, welcome to the IMS GATE Academy. I hope you are doing great, well and fine. So as you are already aware that we had started the foundation course of the various subject and with respect to the various stream, and in this we had already covered the 3 lectures. All right, we had already completed the 3 lecture and this is the lecture number 4. So those who have not watched, after completion of this session, definitely you will going to watch. So definitely you should go and watch that lecture as well. All right, so myself Nikhil Gaurav, and I'll be covering here the electrical machine. Now in the very first class, that is lecture number 1, we had completed the syllabus related to the GATE exam and also with respect to the academic. All right, so those who are not having a good idea about the syllabus and the important topic, you can say, you will start from the lecture 1. Definitely you will going to have a good idea about the syllabus. In the lecture 2, we have seen the electrical material. So what kind of electrical material is required or a benefit if you're going to choose such type of electrical material in our electrical machine. So we have seen that by choosing a copper will give you a vast variety of you can say the advantage. Okay, so because of that, a copper is a prime choice for making an winding of in an electrical machine. In the next part, we have seen that we have one more type of conductor. You can say an aluminium, but that aluminium, due to some certain disadvantage and due to advantages, some kind of advantages over the copper, we have chosen the aluminium in the power system. All right, the overhead wire that we are making for connecting a tower. All right, so by making a linking, to make a linking between the tower, we are connecting by aluminium wire. All right, or you can say the overhead wire. So the prime choice of such conductor is aluminium in the power system. So that was the lecture number 2. In the lecture number 3, we have seen the magnetic material. All right, so in the magnetic material we have seen 4 category basically: paramagnetic, diamagnetic, ferromagnetic, ferrimagnetic, and the ferromagnetic was one of the prime requirement, or you can say the prime element, the ferromagnetic material, such that if you're going to choose, you will going to have a great advantage in your electrical machine. So those who have not covered, please go once this lecture will going to be over. Definitely start with the lecture 1, then go to lecture 2, lecture 3, and so on. Definitely you're going to have a good idea about the electrical machine. All right, so this is the lecture number 4, and we're going to cover the rules and the laws of electromagnetism. So one request is that please do share the session with your friends so that they should also join the live session, and they will going to have a maximum advantage of the session. And whatever doubt you are having, definitely I will going to resolve all those doubt within a span. All right, so please do share the session link and like the session as well, and also do subscribe our YouTube channel IMS GATE Academy, and also press the bell icon so that whenever we are going live, definitely we're going to notify instantly. So let us start with the rules and the laws of electromagnetism, and here onward basically we are going to enter into the machine. All right, so without the rules, without having a good idea about the rules and the laws, one cannot imagine about of the electrical machine. All right, so everything is hovering around, you can say, about the around the rules and laws. So let us start with the rules in the electrical machine. So basically we have 3 types of rule. First one, Fleming right hand rule, or you can say the Fleming right hand palm or thumb rule. So definitely this you have studied during your 11th and 12th, and also some student have also studied in 9th and 10th in the physics. All right. Why we are using this, I will let you know. But as of now, let us see what are the rules here. Second one, Fleming right hand rule, and this is one of the most important rule in the electrical machine. Okay. And the third one is the Fleming's left hand rule. Anyway, all the three rules are important, and we'll see each and every one in detailed manner. And if you're having any doubt, please do let me know. Vipin Mishra, fantastic lecture, sir. Thank you, Vipin. So, see here, my friend, we will start with the rule 1, which is Fleming right hand, palm or thumb rule. Both are same. Means in some book we used to refer the Fleming right hand thumb rule, or in some other book we'll refer this rule as Fleming right hand palm. So all are same, only the notation are different. So in this, as I've said that we have two types. First one is basically whenever a current is flowing in the conductor, then that current will going to generate a magnetic field. So the possibility here is two. What is that possibility? The first possibility is that a current can flow in a straight wire or in a straight conductor, and the second one, a current can also flow in a circular conductor. So depending on that, we have two rules. So the rule A in the Fleming right hand thumb or palm rule, the right hand rule is basically a principle in electromagnetism that is used to determine the direction of magnetic field. This is very important word, the direction of magnetic field in a straight conductor carrying current. So see here, this picture. This is this blue one. This blue one is basically what? A conductor in which a current is flowing, which is given by this direction, white one. So this white one is basically a direction of current. Then the steps will tell you how you are going to find the magnetic field. So the first step is extend your right hand and point the thumb in the direction of electric current which flow inside the conductor. So here current is I. Next, then the forefinger wrap or curl around the conductor which point in the direction of magnetic field lines. So see here, this is the straight conductor and current is flowing from left to right. So put out your right hand in the direction of conductor and in the direction of current, point your thumb. So the thumb will indicate the direction of current. Now this forefinger, this total forefinger will wrap up in such a direction that it will going to give you the magnetic field. So see, this is conductor, this is current direction. So when you wrap this one, then this forefinger is the movement of this forefinger is such that it is coming, it is going inward, means inside the board, and it is coming outward towards you, like this it is coming. Done. So what is the direction here? Direction here is like this. So this all red line is basically what is magnetic field. Done? Any doubt? So I have taken some example and let us practice or let us do a master basically in this Fleming right hand rule. So this is a conductor. This is question 1 and question 2 basically. This is a conductor, or means a conductor can be a bending of type or can be a straight wire. So for generalizing purpose, I have taken a conductor in a bending type. Alright. So let us take the direction of current here like this. This is the yellow one is a conductor, and in conductor we have the current flowing inside this conductor. Now, since whenever a current is flowing, it will going to generate a magnetic field. Basically, how we will going to find the direction of magnetic field? By using Fleming right hand and palm rule. See, the direction of current is in this direction. So point your thumb in the direction of current. Then this forefinger will curve in such a direction that it will give the magnetic field direction. So definitely the direction here will be like this. See, so direction here is like this. Done. Now in the second part, let us reverse the direction of current. This is the current and this is I. So direction of current is, in this case, is downward. So point the thumb, then this forefinger will give the direction of magnetic field. So it will be like this in clockwise manner. This is magnetic field direction and here also magnetic field direction. So it is very clear that whenever we have two direction of current, definitely the direction of current will going to be different in two different conductor. The direction will not going to be a different in a same conductor. So whenever we are having a current in opposite direction, then in such cases the direction of magnetic field also going to change. This is one note point. Let us move to the next part. Here, let us take the current in this direction. What is P? I will let you know, but as of now, let me make the question complete. Let us say this is the current direction, and here let us take the current in same direction, I. Now, this P is what? Basically, this is a point P in which I want to know whether my magnetic field is entering into this P or it is coming out from P. Means it is entering inside the board, what? Magnetic field, or the magnetic field is coming outward from the board. That I need to find. So for this we require one basic, and that basic is very, very simple. I hope definitely you have seen bow and arrow. In Hindi we used to call it as dhanush and baan, isn't it? So whenever you are releasing an arrow, from a bow, so whenever you are releasing an arrow, then arrow will move away from you. So suppose this is an arrow. This is an arrow. So whenever this arrow you are releasing, then this arrow is moving away from you. So you will see the end point or tail of the arrow. So the tail of the arrow will look like a cross. Isn't it? Whenever it is moving away from you. Now whenever this arrow is coming towards you, then you will see the head of the arrow, isn't it? If this arrow is coming towards you, you will see the head of the arrow. So this head of the arrow is look like a point, like this. So whenever it is moving away, it look like a cross, and whenever it is coming towards, you will see a dot, isn't it? A dot. Now let us use this concept here. See, the direction of current is upward, then this forefinger will give the direction of magnetic field. So current is upward and it will give the direction of magnetic field. So this forefinger is moving inside, it is moving inside the board. So it means it is moving away from you, isn't it? Moving away from you. So here a cross will come. Here a cross will come. It is visible. Okay, just a second, let me use different color. it across will come here. Means this tells that in point P or at point P, the direction of current, the direction of magnetic field, not the current, the direction of magnetic field is inside the board. Let us come here. In the second part, the current is same, means the direction of current is upward. So this P, at the P, the magnetic field is coming towards you. Coming towards you means the magnetic field here is dot. Like this. So from now onward, if you find in any book, from now onward, if you find any in any book, if you are going to find the cross and the dot, it tells you the information about the magnetic field, such that cross implies the magnetic field moving away from you and dot implies the magnetic field coming towards you. All right. So let us take let me give this question as a practice question, where the current here is, let me take the current here is this current is I, and let me take here direction of current is I. So please do practice this question, or please do solve this question and comment the answer in the chat box. I will see each and every answer there. All right. So let us move to the next, basically the part B of the first rule. Is that means we have seen a magnetic field due to a current in a straight conductor. Now let us take the circular conductor and let us flow the current inside to that conductor. So what it tells, the right hand rule is a principle in electromagnetism that is used to determine the direction of magnetic field in a circular conductor carrying current. And how we are going to find? Extend your right hand and curl the finger in the direction of electric current, all right, which is I. Then the thumb represent the direction of magnetic field line. So basically this is the reverse of the rule or the method that we have used in part A. In the part A, thumb shows the direction of current and this forefinger shows the direction of magnetic field. Here it is reversed. Here the forefinger will show the direction of current and thumb here is showing the direction of magnetic field. See, so this circular is what? Basically a conductor, and in this conductor the current is flowing in clockwise direction. See, in clockwise direction. So take out your forefinger, curl the forefinger in the direction of current. So like this, clockwise. Then thumb shows the direction of magnetic field. So this is the current direction I. And this is the direction of magnetic field. Any doubt? Clear? All right. So let us move ahead. Determine the direction of magnetic field for the following current direction. So this is an kind of iron bar. This is a second part of the question, and let us make a conductor. Let us make a conductor such that it is wounding, over the iron bar like this. Like this. Okay, and the current here, let us say, is flowing in this direction, and the same current is coming outward from here. Means I am not showing the complete circuit. Assume that we have a battery over here, or an AC source we have here, AC voltage source we have here, and from that a current is flowing. So basically this is what this pen, let us assume that this is your iron bar, and the conductor, this is what? This is what? This is conductor. So this is your iron bar, and the first part of the conductor is such that it is visible to you. The part of the conductor which is not visible to you means it is behind the bar. It is behind the bar. So see, it is visible and it is going backward, and in the direction of current, you will have to see in the direction of current. So it is going upward, and from the back side it is coming downward. So this, curl your forefinger in the direction of current, then thumb shows the direction of magnetic field. So the direction of magnetic field here is what? Is from right to left. So like this. So this is the direction of magnetic field. I hope this is visible. Let me change the color. Done. So in this way, you will going to find the direction of electrical. Nice lecture, sir. Thank you, electrical. So let us take the second case. Now in this, let me change the winding fashion over here. All right. Now how I will going to do? I will now take the wire from back side and it will come forward like this. Like this. So this is the direction of current. Let me take the same direction and we'll see what changes we are going to have. If you are going to change the direction, means if you change the fashion of the winding, what impact it will going to have in the direction of magnetic field, that I want to see. So this is the current direction, I. Done. So this is your iron bar, and at this time the current is coming, at this time the current is coming from back side to front side. So see, from back side to the front side. So this thumb shows the direction of magnetic field. So this is iron bar, from back side to the front, the direction of current it will give, and the thumb shows the direction of magnetic field. So this time it is from left to right. Electrical, very easy to understand, sir. I will share to my friend also, very useful. Thank you, electrical. Please do share and also inform your friend to come live in all the session, not only of mine, also to the of the other faculty as well. All right. So electrical, thanks Nikhil sir. Thank you, electrical. All right. So let us see here. The direction in this case, wait a second, the direction in this case of the magnetic field is from left to right. This is magnetic field. Any doubt? Do let me know. If you are having any doubt, please do let me know. So this kind of a technique we will going to use in finding the direction of magnetic field whenever you are having the current, basically those current can be an alternating current, which is known as AC current, or it can be a DC current. All right, so let us see the next one, which is the second rule. All right, we are done with the first rule, Fleming right hand rule, right hand palm rule, or right hand thumb rule. I hope it is clear to you, and let us enter directly into the Fleming's right hand rule. Now here basically you are going to enter into the generator and the motor part. In the generator, basically the output of the generator is what? Electricity, na? And electricity is basically combined, means the electrical power is basically what? Voltage into current. So this Fleming right hand rule is applicable in the generator, where the output is what? A voltage or current. So whenever you are supposed to find the direction of induced current, or the direction of current, or the direction of EMF, then we will going to use the Fleming right hand rule. Now see, Fleming right hand rule is used to determine the direction of induced current in a conductor. So how we will going to find? By using this step. What makes the difference between the rule 1 and the rule 1 and the rule 2? In the rule 1, the direction of current was given to us, and we are finding the direction of magnetic field. But here we are finding the direction of induced current. Both are different. Please do not assume that the current that we have used in the rule 1 and the current that we are going to have here are same. No, it is different. In the rule 1, the current was from the source current, but here it is somewhat different. Now see here, my friend, how we will going to use the rule? Extend your right hand and stretch your thumb, forefinger and middle finger perpendicular to each other. Perpendicular means 90 degree. So this is your right hand, stretch the thumb, then forefinger, this is forefinger, and the middle finger. Stretch mutually perpendicular to each other like this. See, mutually perpendicular means 90 degree. Now, in the second step, point your forefinger in the direction of magnetic field. Done. And third, point your thumb in the direction of velocity of force. All right, for velocity or force. Then the middle finger point towards the direction of induced current. So what it says, stretch your right hand and the three fingers, thumb, forefinger and middle finger perpendicular to each other. Then this thumb should point towards the velocity or the force, this forefinger towards the magnetic field, and after that the middle finger will give the direction of induced current or the polarity of induced EMF, like this. See this picture. This is your right hand, and you will going to use right hand in this manner. So this is one question, and let us practice with the question here. Determine the direction of induced current. So basically we are having three methods to find the direction of induced current. I will explain each and every method in detailed manner. Please be attentive while I am dictating every method here. All right, do not lose the paces, otherwise it will going to above your head. All right, so let us enter into the method 1, and here this is what? This is the conductor. The blue one is basically a conductor. This is the R, which is a kind of electrical load, because as I have told you, this is used in the generator where we are having the electrical load and means electrical power, so we require voltage and current. This is the magnet. Basically this is the same magnet which is having the north and the south. Okay. See, this is north and the south, and we know from the chapter 3rd, the magnetic field flow from north to south, where the magnetic field lines coming outward from north enter into air, and now it will going to enter into the south pole, whereas inside the magnetic field lines flow from south to north. All right. So this whole thing are air. This is north, this is south, and this whole thing are air. This is what? This is conductor, and in this conductor, the current will going to induce. All right. So let me show the direction of magnetic field. Like this. Just a second. Okay, so this is the magnetic field direction. This is B. Done. Now we require the velocity of the conductor, means the conductor has to move. Now if you see closely, this point is what shows the direction of movement of the conductor. So suppose this is your conductor, and according to this direction, it is coming towards you, and this part is going backward. Like this part is coming towards you, and this is moving backward. So the direction is anti-clockwise, isn't it? The direction here is anti-clockwise. So what Fleming right hand says, that it will going to induce a current. So how will you going to find the direction of current? See, use the Fleming right hand, stretch your this three finger perpendicular to each other, where thumb shows the direction of velocity of the conductor. So since this portion is moving outward, so it is towards you. The thumb will show the direction of velocity which is towards you. Then this magnetic field should point towards the direction of magnetic field like this. So how you will going to place these two fingers? Velocity of conductor towards you and the magnetic field. So this middle finger is upward, which gives the direction of induced current. So like this, magnetic field, the forefinger, thumb, velocity of conductor, then middle finger gives the direction of what? Induced current. So this is current I. This is the current I. All right. I am giving you one task. Since this is coming outward, so this will going to be move inside, isn't it? It will going to move inside. So here the rotation for this conductor is what? Like this. Rotation for this portion is like this. So try to find the direction of current here. Definitely, if you're going to use the basics of Kirchhoff's law, the current can flow only in the closed path. So assume this since this is a closed path, so from here it is going upward. So definitely here it will going to come downward. But please do verify by using the Fleming right hand rule. So this is what? This is method 1, in which you will going to find the direction of induced current. Now let us come to the method 2, that is the cross product. So here I am going to use the basics of electromagnetic field theory, or simply electromagnetic field. So here I will going to, wait a second. Anyway, so here I am going to fix the direction of every quantity. Direction of every quantity. Magnetic field is in this direction. Conductor movement is outward of the board. Then it shows this the middle finger shows the direction of what? Induced current. So let me place all the thing. This forefinger is basically what? A kind of axis. Like XY axis we are having now, which is known as 2D axis. Similarly, we are having 3D axis. X axis, Y axis and Z axis. These three are placed perpendicular to each other. So this is an X axis. Sorry, this is an Y axis. This is an X axis. And this is your Y axis. Sorry, actually, sorry, Z axis. Just a second. Okay, this is X axis. This is Y axis. And this is Z axis. Okay, please do write the axis in this manner. If you interchange, like if you interchange X and Y, then everything will going to be wrong. Always make the axis in this fashion. All right, where the angle between every axis is 90 degree. This is 90 degree. It is not possible to make a 3D diagram in a board. So please assume this is the 90 degree. All right. Now, what is the direction of velocity here? Direction of velocity for this part, it is moving outward, means outward of the board. So in this axis, it is represented by X axis. In the XYZ plane, the direction of velocity is in the direction of X axis, means it is outward. So can I say V here means V vector is basically, sorry, V vector is basically magnitude of a vector and direction here is what? In AX direction, which is in X direction basically. This AX implies the direction of what? Velocity. Now B, this is in Y direction. This is B is magnitude and this is in Y direction. So AY. Done. Now, according to the rule, what it says that AX cross AY equal to AZ direction. AY cross AZ equal to AX direction and AZ cross AX equal to, sorry, this is axis. This was X and this is AZ into AX equal to AY direction. Let me give you a trick to remember. Write AX, AY and AZ like this. Like this. And rotate or move in the clockwise direction. So you come with two direction, AX and AY, or two axes, AX and AY. So you are left with what? AZ. So AX into AY give AZ. Similarly, AY into AZ gives AX, which are left, and AZ into AX give what? AY. So in this in this way you can remember the shortcut. All right. Now how we will going to find? See here the velocity is in X direction and magnetic field in Y direction. So your EMF, let me use different color. So your EMF, which will going to produce a current. So EMF is basically V cross B dot DL. This is the expression of induced EMF and it will going to produce the induced current. So see, V is in which direction? AX. This is in AX direction into magnetic field is in AY direction. And this DL is what? Scalar, any length. All right. So the resultant of this two will give the direction of EMF, which will produce the direction of which will produce the induced current. So AX into AY is what? Is AZ. So basically this gives you magnitude of EMF. This is magnitude of EMF which is in which direction? AZ direction. So this produces your induced current. Let us verify. See the current I. It is in upward direction. Here Z axis is upward direction. Done. So in this way, by using these two methods, you can find. What about third method? This is a direct method where we can directly use our concept to find the direction of induced EMF or current. How we will going to use? See, use your right hand and place your forefinger or the complete finger of your right hand in the direction of velocity. First, the all fingers of the right hand should point towards the direction of velocity, isn't it? So it is moving outward like this. It is moving outward, and this all finger has to be now curled in the direction of magnetic field. What is the direction here? North to south. It is in this direction. So this all 5 finger have to curl in the direction of what? Magnetic field, which is in this direction. Then this thumb will show us the direction of induced current. So velocity here is outward. Curl this forefinger in the direction of magnetic field like this. Then thumb shows the direction of induced current, which is here upward. Done. Let us use the same concept, means the third rule, which is the third method, which is direct method. Here basically for this conductor, the movement is inside the board, isn't it? So velocity is in this direction, inside the board. But the direction of magnetic field is what? From left to right. So curve this forefinger in the direction of magnetic field like this. Then thumb shows the direction of induced current, which is downward. So here I have proved you the direction here will be downward. Then we can also verify by the method 2. Here velocity is what? Is inside. Means for the outward we have taken plus AX. For the outward we have taken plus AX. Then for inside we need to take minus AX. Let me prove here. Minus AX. For the velocity, EMF is what? V cross B. So minus AX into magnetic field is in same direction, that is AY. That is AY. Let me take minus outside. Can I write this as AX into AY? What is AX into AY? AX into AY is AZ. So this gives you minus AZ. What it means? For this conductor, if the conductor is moving inside the board and the magnetic field is in this direction, then induced current in this conductor is in minus AZ direction, minus AZ. Since this is taken as plus AZ, so minus AZ means downward. Clear? So this you can do from the method 2. So I have explained each and every method, method 1, method 2 and method 3. Whatever method you are comfortable, you can use in your exam, like in the academic, also in the GATE exam or anywhere, whatever exam you are having. If the question is related to the direction of induced current, you will going to use any of the 3 method. Whatever method you are comfortable, you may choose. So let us move to the practice problem. This is a practice problem, and in this I have changed the direction of movement of the conductor. Earlier it was anti-clockwise, but this time it is what? This is clockwise. So please do find the direction of induced current in this part and this part. Alright, so this is a practice problem. Let us come to the next rule, which is Fleming's left hand rule. So since the right hand rule is used for the is used in the generator, then the Fleming left hand rule will going to use in the motor. All right, and what it tells, basically in the motor, what we have, the output as what? Mechanical. The motor will have the output as mechanical, and mechanical will have two kind of movement, either a linear movement or a rotational movement. So every machine basically we are having the rotational movement. So those movement is basically what is will going to give some kind of force or some kind of torque, and the direction of torque or force is given by the Fleming left hand rule. Let us see. The Fleming left hand rule is used to determine the direction of force or torque experienced by a conductor. So what it tells that whenever a current carrying conductor placed under the influence of magnetic field, then it experiences a torque. Earlier in this method, what this E equal to V cross B implies, it tells that whenever a conductor is moving, conductor is basically is having some length. So whenever a conductor is moving inside the magnetic field, whenever a conductor V's velocity is moving inside the magnetic field, which is B, then EMF will going to have inside that conductor. Whereas in the Fleming left hand rule, whenever a conductor is carrying a current and it is placed inside the magnetic field, then it will experience a torque. So to find the direction of that torque or force, we will going to use the Fleming left hand rule. All right. So my dear friend, E equal to V cross B, and here F equal to IDL cross B, I will going to derive in the next lecture, that is lecture number 5, which is on tomorrow. But as of now, let us understand how we will going to use the left hand rule. So here we need to use this 4 steps. The first step is extend the left hand. Earlier we have used the right hand to find the direction of current. This time I will going to use the Fleming left hand rule. So extend your left hand and stretch your thumb, forefinger and middle finger perpendicular to each other. Point the forefinger in the direction of magnetic field. So in the right hand rule and in the left hand rule, the direction is given by the forefinger. All right. Point your middle finger in the direction of in the direction of electric current. So this time this middle finger will show the direction of induced current, which is same. Then the thumb point towards the direction of force. So if you going to follow this step, then this thumb will show the direction of what? Direction of force or torque. See this is your left hand, motion of conductor, magnetic field, and this middle finger is current. Let us do some practice with this question. Determine the direction of this is the direction of force experienced by a conductor AB. Okay. So let us take this part is a conductor which is having a portion as AB. All right, this blue one is basically completely is what? Your conductor, and this is the one portion of the conductor which is AB. And here we need to find the direction of what? Direction of force. So this is your voltage, this is not a velocity, this is the battery. Okay, and from this battery a current will flow. So the current will flow from the positive, means the current will move out from the positive terminal and it will enter into the negative terminal. So what is the direction of current? This is basics of your network only. This will be the direction of current. See the positive terminal of the battery. So current will move like this, and it will go like this in this conductor, and in this conductor the same current will move downward like this. And in the same way, the direction of the direction of magnetic field is from where to where? From north to south. From north to south, like this. This is the magnetic field direction, B. Done. But I am finding the direction of force for the portion AB. Then I will give you a task. I will give you a task to find the direction of force or the torque for the portion CD conductor. For the portion CD, which is the conductor. Now let me find for AB. See, I will going to use first Fleming right hand rule. So stretch your forefinger. Basically, this rule is give you the information about force, which is equal to IDL cross B, like this. This force is basically what? IDL, extremely sorry, IDL cross B. So IDL will be taken together. Why? Because this DL is what? Conductor length, and a current can only flow in the conductor. So this is the reason why we always write I and DL, means DL is what? Some a small amount of length. So I and DL will taken together always. So, and this 3 will give you the direction of force. Now see, current here is in upward direction. Done, which is basically flowing inside the conductor, and magnetic field is in this direction from left to right. So take out your left hand, point your middle finger in the direction of current, which is upward, isn't it? Then middle finger, then your forefinger should point towards the direction of magnetic field like this. Okay, wait a second. Current is in upward direction, like this. This is a current direction, the middle finger, the forefinger in the direction of magnetic field. Then this thumb will shows the direction of force or torque. So this thumb is pointing inside the board. So can I say here the movement here is down, what to say, the inside the board, like this. See, upward direction, this current in conductor AB we are finding the direction of rotation. So this conductor AB current is upward, magnetic field from left to right, then thumb point towards the rotation, means this thumb gives the rotation of the conductor, which is inside. So it is, this portion will move inside like this. So I have shown inside, So basically the rotation here is what? Rotation here is clockwise rotation. All right. So rotation of conductor is clockwise. Means the complete rotation. Let me give you a task. Please find the rotation here. Whether this portion CD is moving inside the board or it is coming outward of the board. Now let us use the method 2, which is the cross product. Okay, so this is x axis, this is y axis, and this is z axis, and all are mutually perpendicular. Now, according to this formula, IDL cross B. So, IDL is basically in upward direction, and this is given by z axis, isn't it? So, this is in AZ direction. Which one? Ideal. Please do not interchange, otherwise you will going to have the wrong answer. Ideal is in upward direction. This B is what? Magnetic field, which is in this direction, and it is given by y axis. So, AZ into AY. AZ into AY. So, this AZ into AY from this part, AZ into AY, where it is? See, if AY into AZ is AX, if AY into AZ is AX, and if you interchange, this means that it will going to give the minus AX direction, isn't it? This is for the positive, and if you interchange these two, you will going to have the opposite direction. Say like this, AX into AY is AZ, then let me use different color. Here AY into AX will give you minus AZ. Similarly, AZ into AY gives you minus AX, and AX into AZ will give you minus AY. Just a second. Okay, so come here. All right, so AZ into AY will give the answer as minus AX. Minus AX. So, plus AX means outside, then minus AX means inside. So, the same direction we have got for part AB, for the portion AB. Any doubt in this? Done. So, minus AX, this implies direction is inside the board for me, and for your paper, for you inside the paper. Done. And what about direct method? See, in the right hand rule, we have used the right hand. Then in the left hand rule, we are going to use right hand, not the left hand. All right. So, the direct method is basically we will going to use a right hand for both the rules. All right. Rule 2, that is Fleming right hand rule, and for the third rule, Fleming left hand rule, we are going to use the right hand only. See, IDL cross B. Place this forefinger, this total forefinger in the direction of magnetic field, in the direction of current, in the direction of current, and curl this forefinger towards the direction of magnetic field. So, ideal magnetic field is like this, na, direction, curl. So, this thumb gives the direction of torque, which is inside the board or inside the paper, which we have got here by using the cross product. Any doubt? So, you can use any of the three methods. So, this is a practice problem, and here one difference is I have interchanged this magnet pole. Earlier it was north to south, north was here, South was here, and this time south and north I have swept these two poles. Now let us come to the laws in the electrical machine. So we have completed the all the rules of the in the electrical machine. Now let us enter into the laws in electrical machine, which is very important. Those who have already studied the electrical machine, they knows what are the advantage, what are the vast advantages we are having by the Faraday's laws. All right, by the use of Faraday's laws, what are the advantage we are having in the electrical machine. Now what is Faraday's laws we are having? Basically we have two laws. Lenz law, what is the Lenz law, I will let you know after a time. First let us understand what is Faraday's laws. What Faraday says that whenever in a circuit we have a change of magnetic flux linkage, whenever in a circuit we have a magnetic rate of change of magnetic flux linkage, then the EMF will going to produce inside the conductor. So this Faraday's laws tells that E proportional to d phi equal to d phi by dt, which is written here in the form of statement. Done. But let me explain you some what in a little bit detail. First thing, we'll take a concept from the lecture 2, which is of magnetic flux. Let us first understand what is flux. Let us first understand what is flux. Flux is basically a flow. Means a water is fluxing, water is flowing. So in a simple manner I can represent the flux with flow, but let us keep ourselves in the electrical machine. So flux is basically what? A flow. Then what is magnetic flux then? This all we have seen in lecture 3. Okay, magnetic flux. So what is this magnetic flux? This magnetic flux is basically what? Flow of magnetic field lines. All right. So this magnetic flux is represented as phi, okay, and this is proportional to number of magnetic field lines, number of magnetic field lines. Done. Now whenever please listen me very carefully, this flux is basically what? Proportional to the number of field lines. So can you please tell me the unit of this number of lines? Any unit? No. We cannot give a unit for any particular lines. All right, I am not saying about centimeter, meter. No, please let me know the unit of the magnetic field lines, or lines or the unit of this field lines. It is not possible to say. So we are not having any, as of now we are not having any unit for this magnetic flux. But once you remove this proportionality sign, we will going to have the unit. See, this phi becomes equal to B times EA. Very important expression. A magnetic field intensity times B is a magnetic field intensity times passing through an area will give you magnetic flux. Just a second. Done. Now what Faraday says, now see here what Faraday says, Wait. Let me reduce the font size. Now, what Faraday says us that if a magnetic flux which is phi passes through and turns of a coil, then EMF induces in a conductor. So this is the statement of the Faraday's. But here one thing we should understand, that psi is what? Basically N into phi, which is flux linkage. So the number of flux linking the N turn of coil is known as flux linkage. Means how many flux are linking the conductor, or sorry, linking the number of turns of a coil. Alright, so this psi is basically N into phi. Now when you represent this in mathematical manner, you will get your EMF like this, E equal to d psi by dt. Replace psi with N phi, where N is what? Number of turns. So it will be constant always, isn't it? Over the time, the number of turns will not going to change. Whatever turns or whatever amount of turns you have made already, it will not going to change with respect to time, isn't it? So this N is what? Basically N is constant, so it will not going to affect by the time variation. So this N becomes constant, so you will have N d phi by dt. So the statement the statement that I have written here with the green one is basically related to this d psi by dt, whereas in some other books you may find the Faraday's laws like this: a rate of change of flux will induce an EMF. So both are same. This gives the rate of change of magnetic flux and this gives the rate of change of magnetic flux linkage. Both are same anyway. Alright, so let me reduce the font size. Okay, so this is what? Basically, I hope this is visible. Okay, so E equal to d psi by dt, which is equal to N d phi by dt. So just place this psi here, you will get this expression. Now this is what Faraday's laws. Now EMF can only be induced whenever we are having the magnetic field B and a conductor. EMF can only induce in a conductor. This means that the requirement to have an EMF, is what? The first one, this is the requirement. Until and unless we are having this three, you cannot having to have any EMF. The first one will be the magnetic field, which produces the magnetic flux, basically magnetic field. Second one, a conductor, or let me write conductor simply. Conductor. So this magnetic field is B or phi. Some may represent with B or some may represent with phi. And a conductor, and the third one which is very important is the relative variation. Relative variation between conductor and magnetic field field. All right, so this relative variation is very important. Until and unless you are having this, you cannot able to produce an EMF, even though you are having these two quantities. All right, so the relative variation can be generated into two manner. The first one here is, means under this relative variation, a stationary conductor and rotating magnetic field means a conductor is not moving but a magnetic field is moving. So definitely in between these two we are having some relative variation. What do you mean by relative variation? Means there is a difference between the movement, you can say, means simply a movement between the conductor and the magnetic field. So in the first way we can have a relative variation which is basically used in transformer. This is used in transformer. Okay, and the second one is interchange these two. A stationary magnetic field. A stationary magnetic field and moving conductor. So here magnetic field is stationary but the conductor is moving. So this type of relative variation we are using in DC machine, induction machine, just a second, and synchronous machine. Done. So if you are having this all three requirement, sorry, if you are having all these three element, then you are going to have the EMF inside the conductor. All right, and where the third point is very important. Until and unless, even though you are having this two, if you are not having if you are not fulfilling the third requirement, you cannot able to produce the EMF. Done. Now what is the drawback? Drawback of the Faraday's laws is that it can tell the magnitude of EMF, means what is the value of EMF that will be going to induced in the conductor, like 1 volt, 2 volt, 3 volt and so on and so forth. But it cannot able to tell you the polarity. Suppose, see, I told you have a battery which is having the value of 2 volt. Now, can you able to tell me whether the plus sign will come towards the left side or the right side? No, isn't it? It is not possible to tell. If I give you a 2 volt of battery, can you able to tell me that the positive polarity will lie towards the left side or the right side? It is not possible to tell. So, in the same way, the Faraday's laws will tell you about the magnitude, which is 2 volt here, but it cannot able to tell you the direction of the induced current or the polarity of the induced EMF. Therefore, a lens comes into a picture. So, Lenz's law helps the Faraday's in such a way that use the Lenz's law concept, and you will going to have the polarities. Now, what Lenz's law says that it tells us the direction of induced EMF in a conductor or circuit is such that it opposes the change in magnetic flux that produced it. Do not get worried, we will take one example and from there we will understand. Or in other words, when a magnetic field is changing, the induced current flows in such a direction as to produce a magnetic field that opposes the change in original magnetic field. So, in a short manner, if I want to say that E, which was n d phi by dt, and d phi by dt, this was the Faraday's laws, and it opposes the magnetic flux that is produced this EMF. So, opposes means what? In that you will have to place a negative sign. So, this negative sign implies the opposition. Okay. So, let me give a note point. Note, negative sign implies the opposition offered to cause. Means the EMF which is produced by some cause is opposing it. So, in a nutshell, Lenz's law, Lenz's law is what? Effect opposes its cause. In a simple manner. So, the cause here is that the EMF is produced by which quantity? By whatever quantity the EMF has been produced is the cause, and this cause will going to be opposed by the effect. all right, and this opposition is is represented by a negative sign in the Faraday's law. So this makes the equation to be get complete. All right, now let us take one example. Okay, just a second. Let us take one example here. Find the magnitude or simply find the direction of induced EMF or current. Okay, so let me make a diagram first. Okay, so this is a kind of your iron bar. Okay, and in this, let me wrap a conductor like this. This is your conductor. Now let us take the external magnetic field. External magnetic field in this direction. Wait a second. This is phi. This is phi external. Okay, so this is the external magnetic field. So this is produced by some external source. Now see the direction of external magnetic field. It is downward, isn't it? It is downward. Wait a second, it is about to complete. Please wait. It is downward. Done. Now effect opposes its cause. So due to this phi external and from the Faraday's laws, an EMF will going to be induced. This is flux and this is a turns of a coil. One turn, second turn, third, fourth, fifth. So 5 here, this is 5 d phi external by dt. So definitely your EMF will going to induce, isn't it? Your EMF will going to induce. So the polarity of E will be given by what? Will be given by the Lenz's law. So effect opposes its cause. So here effect is what? sorry, here cause is what? Cause is the production of EMF, but this happened when? This EMF is induces when? Whenever we are having this phi external, isn't it? Whenever we are having this phi external. Just a second, let me shift somewhat upward. Done. So this phi external has to get opposes. Now how it will going to oppose? See, the phi external is in downward, then opposition means the flux has to be upward, means whatever the flux has going to be induced, it will going to oppose this phi external, isn't it? Then only it will going to say na opposition. So see, since it is downward, then to have the opposition here, for opposition we require the EMF which is induced EMF basically in upward direction. In upward direction. So this one is basically what? This one, this is phi induced, sorry. This is phi induced. So if you closely see, phi external and phi induced, phi external and phi induced are in opposite direction. So it is what? Opposition, means the net flux is what? It's going to be reduced. Now to get this phi induced in such direction, what should be the current then? What should be the direction of current that we are going to have such phi induced direction? The flux can only be produced whenever we are having the current, na? So this phi induced will going to be induced by the induced current. So to get this direction, what should be the induced current which is going to be flow in this wire? So again we will going to use the Fleming right hand thumb rule. Place your thumb in the direction of magnetic flux, which is what? This phi induced in upward direction, then this forefinger will give you the direction of current. Alright. So this phi is upward direction, phi induced basically, then forefinger will give the direction of current. So just a second. So from left to right, sorry, from right to left, suppose if I am standing like this, so from right to left means in this the current will flow, isn't it? And from back side it is coming like this, from in this direction. So the direction of current should be like this here, and it should be like here. See, let me change the color. Wait, let me change the color. Direction will be like this. From back side, it is from right to left, and from front side means from front side it is from right to left, and from back side it is from left to right, like this. So it is go back, sorry, this current will go towards the back side, and it will come at the front in this manner. The direction of the current will be like this, isn't it? Now here we have got the direction of induced current, but what about the polarity? So for the polarity, we will assume the fictitious resistance. How? See, I will going to place here fictitious resistance, which is R fictitious. This is the fictitious resistance. Now this current I this current I, it will going to enter into this fictitious resistance. So whenever it will going to enter, means whatever current will going to enter into the element which is a resistor, capacitor or inductor, the first whenever it is entering, the first point will be represented as a plus, like this, and here the end point is represented by minus. So if I should have named this terminal as A and this terminal as B, then your EMF EAB, before applying, see, before applying the Lenz law, the EMF was N d phi by dt, before applying the Lenz law. But where N is what? 5, and d phi by dt, where phi is what? Net flux. So phi external minus phi induced, because both are opposite, phi external minus phi induced. This is the net flux, and the direction will be what? Sorry, and the polarity will be what? EAB, A as plus and B as minus. So this will give you, if you apply the Lenz law, it will give you EAB as 5. Sorry, anyway, I have already written 5 d phi by dt, which is phi external minus phi internal. So this is what? This is Faraday's laws along with the Lenz law. Done. So in this manner, you will going to find the EMF magnitude as well as the polarity of the EMF. So please keep please keep one thing in mind, that whenever you are trying to find the polarity, please insert the fictitious resistance, and from there you will judge the direction of current and the polarity of the EMF. Done. So with this we have completed the today's lecture, which is lecture number 4, and I hope everything is clear to you. So guys, please do like the session and share the session with your friend, and we'll see you tomorrow in the next lecture, which is lecture number 5 basically, and in that we will going to study the type of EMF. We have seen now what is the EMF that we are going to have. So in the tomorrow's lecture we will going to start with the type of EMF, force on the conductor, means how the force will going to be have in the conductor, and also one more thing, that is dot convention. So tomorrow class is also very interesting and you can say very important. Alright, so bye bye and take a very good care of your health.